Uh, Good afternoon, everyone. I hope you can hear me. If you can hear me, can you just say yes in the chat box? Okay, so you can hear me, there is no problem. Yes. As far as I know that we are expecting a little bit more people, but meantime, can you tell me, I do not know anything about you, your background. Can you just say, what are you studying? Is it bachelor's, master's, and which stream? Please put it in the, okay, BSc Biotechnology, BSc Chemistry. Okay. Please go ahead. BTech, Biotechnology, final, B Pharm. Okay, there is B Pharm, M Pharm, MSc Biotechnology, B Pharm as well. Okay, BSc Biotechnology. Okay, B Pharma. Anything else? Anybody other than these? Okay, and BSc microbiology. BSc. Okay, great. Okay. Right now, how many are we? 44. We just wait for 2 more minutes and then we can start. Okay. If there's last anyone else who is yet to join, you just wait. Anyway, today's class will be just the introduction to nanotechnology. And also because there are a lot of people who have not yet subscribed, I will also give an overview of what we are going to do in this next 12 classes. So it will be an overview of the whole course as well. So let's just wait for 2 minutes. Somebody is asking, after the class, will there be notes we can refer to? As far as I know, Mr. Revant, sorry, the classes are all getting recorded. So I think you can go back and watch it, rewatch it if you miss something. In some classes, I'll definitely give some papers to read, but not today. Okay, we will soon start. 1 minute. Also, is the screen visible to you? And the slide, or should I make it bigger? Is it visible? Yes or no? Okay, great. Some more answers would be helpful. Okay, almost everybody says yes. If somebody cannot see it, please write it. Okay, seems okay. Okay, so let's start today. So firstly, let me introduce myself. I am Dr. Dipankar Kalita. I have done my PhD in nanotechnology, and I will show you in which field I had done my PhD and my PhD work, but not today, because that will be going a bit deeper. But in later classes, I will definitely show you what we do, what you can expect when you start, when you want to go deep in nanotechnology. And also, there are few, it's when you go deep in nanotechnology, there is one thing you have to keep in mind is that there is no chemistry, biology, physics, okay? They all come together, okay? They all come together, and this division, the traditional division of sciences, physics, chemistry, biology, they all break when you want to do nanotechnology, okay? And I will demonstrate why it breaks, and also why is it important to break, okay? And we will, when we go to the examples, and how we will know why chemistry, biology, and physics, they all come together in order to understand nanotechnology, okay? But before that, let's start with the definition, okay? So what is the definition of nanotechnology, okay? So if you look at the screen, there are 3 points that are important. So first point says research and technology development at atomic, molecular or macro levels in the length scale of approximately 1 to 100 nanometer, okay? So here the point that you should remember is that the range on which we will work is between 1 to 100 nanometer, okay? So most of the time when we refer to nanotechnology, this is one of the way of looking at it, okay? The second thing is that what is the purpose, okay? So purpose is creating and using structures. So structures here by mean structures which are in the range of 1 to 100 nanometer, okay? Structures, devices, and systems that have novel properties and functions because of their small size or slash intermediate size, okay? So why do you have to make, here the question that is answered here is that why do you have to make this material so small, okay? What is the point? Because when you make things small or big, it needs energy. It needs a lot of effort to do it, okay? It doesn't happen just like that, okay? So why do you have to go to this small size, which is 1 to 100 nanometer, which is very difficult to see, okay? You need special electron microscope to see these objects, okay? And these electron microscopes itself are millions of dollars costly, okay? The microscope itself, the microscope that we use in our biotechnology lab or in the school, it is light microscope, which is not so costly, okay? Few thousand euros, okay? Or let's say if in rupees, it's let's say 10,000 to 1 lakh or 2 lakh rupees, okay? But here, when you go to electron microscope, it easily crosses 1 crore rupee, okay? Even the basic one crosses. So why do you need to make this effort? So here, the purpose is that you get certain novel properties, okay? The word is here, novel properties or functions that you don't get in other structures. You get these novel properties only because of their small size, okay? Because of their small size, these novel properties start to exist, which is otherwise not existing in bulk material, okay? So this, because of the special properties or functions, we have to make this effort to go to nanoscale, okay? And then what is the purpose of human being in science, okay? As a human race, what is the thing that we always try to do, okay? Always the goal of human being as a race is always that we should be able to control nature, okay? That is the main purpose of why human beings study science, okay? You study the science, then you develop technology to control certain elements, okay? So here, what are we trying to control or manipulate? Okay, here we are trying to manipulate the material at atomic scale. Okay, this is very important. It is so precise that we are able to manipulate device or any structure at atomic scale so that we are able to get this novel properties. Okay, I hope you understand this. I hope you understood these 3 points. Please say yes or no. If you want me to repeat, please write repeat in the chat box. Okay, understood. Anybody wants me to repeat, please write repeat in the chat box. Okay, Somali. Okay, I'll repeat again. Somali. So we need to define define what is. So for Somali, I'll just repeat it a bit fast. Okay. So when we talk of in science, we have always a definition. Okay. Otherwise, people will misunderstand each other. Okay. So we need to define what is nanotechnology. Okay. Something, it's not that something we cannot see. We cannot see atoms and we cannot see nanostructures with our eyes. Okay. So, but still we need to define the range. Okay. So how we are defining the range is that is between 1 to 100 nanometer range. Anything that is within this region, we call it nanostructure, device, or system. Okay. But why do we have to make such a big effort to make devices at such small scale? Okay, it's not easy. You will understand in future classes. It's not easy to make them. Okay, it takes a lot of understanding, lot of precise instruments, and lot of control. Okay, we did this only to get this special novel properties or functions, and by doing this, we are able to control and manipulate anything devices at atomic scale. Okay, so what are the some of the very some examples in today's that we can show it. Okay, so here is one of them. Sorry, let me try to make it a bit bigger. Okay, so now we have cycles that are using nanotechnology. Okay, why? Okay, so have you I do not know, most of you might have seen some cycle races in some part of the world or somewhere. Okay, you won't believe those cycles are costlier than bikes. Okay, the bikes that you see in India, the roads, the diesel petrol bikes, they're even costly. These cycles are even costlier than them. Why? Because they are having nanotechnology in the frame. Let me see if I can annotate. Yes. Okay, they are using nanotechnology to in this frame. So why is it important? Okay, so using here in the bikes today, they are using graphene and carbon nanotube. Why? They are getting when they see that you are using graphene or nanotube, they find that the cycle bike is much more lighter. Okay, it's so light that you can pick it up with 2 fingers. Okay, but just because it is lighter, it doesn't mean it's very weak. Okay, in fact, it's stronger than normal bikes. Okay, the strength of the bike is even stronger, and because they are lighter, stronger, they are faster. Okay, you are able to ride it much faster than the normal bikes. Plus, you can make it even smaller if you want. Okay, sometimes nanotechnology allows you to make devices which are smaller. For example, this bike can be made with smaller material, which makes it even lighter. Okay, and moreover, it's in spite it being smaller, lighter, it's even more durable. Okay, before I don't know if you have seen some hero cycles, the ones very old ones, they're made of iron. Okay, they are very heavy, and plus because there is iron, they rust with time. Okay, so therefore it becomes bad. So these are some properties. Let's look at more properties. Okay, let's go to the next page. Okay, so before we we go ahead, we need to understand in our mind. Okay, there is some question. Nanotechnology can make products hydrophobic, right, sir? Yes, you can make it hydrophobic or philic, both of them. But I will give you an example towards the end of this class about hydrophobicity. So before we go ahead, we should understand what is this size. Okay, you should, whenever you talk to anyone about nanotechnology, this size should be in your mind. Okay, so let's go ahead. So 1 meter is something like this. Okay, this is a plant with a lot of flowers, and then you can measure what is 1 meter. Okay, 10 centimeter is this leaf. Okay, roughly the rough size. Okay, and then on top of the leaf there is a small bee. Okay, that bee is roughly 1 centimeter. Okay, this is the bee. And then if you look closely at the eyes of the bee, okay, the orange part, you will see something like this. Okay, and then it's small elements. You see there are small dots. I don't, let me try to zoom it a bit more. Can you see small dots here? These small dots are roughly of the size of 100 micrometer. Okay, and then if we zoom in, okay, if we zoom in into these dots, okay, there are even smaller dots. Okay, okay, there are even smaller dots. Okay, that these are 10 micrometer. Okay, then if we zoom more, okay, but here in this picture, can you see some small lines like towers? Okay, these are not very visible in this, but if you go to the next here, you'll see in between these small dots there are some small towers. Okay, very like a small needle like figure coming out. Okay, in this picture it's not so visible. Okay, but if you zoom in, it becomes visible. These small towers you can see. Okay, this is roughly of 1 micrometer. The breadth, not the length, but the breadth is roughly 1 micrometer. Okay, now if you look at the, sorry, in this case it's not the breadth, it's the length. The length is just 1 micrometer. Okay, but you cannot see anything at the bottom. The bottom is not very clear. What does it look like? But then if you zoom in, you see the bottom is not, from in this picture, the bottom part here, let me draw it again. Here at the bottom part looks very smooth. Okay, it looks very smooth. Okay, very polished and smooth. Okay, but if we zoom it, you see it's not smooth, it's very rough. Okay, it's very rough. Okay, so that this length here, this length here is roughly of around 100 nanometer. Okay, this is 100 nanometer. Okay, we are slowly coming in the range of our definition of around 100 meter. Okay, now can we zoom more? Okay, the question is, can we zoom more? The thing answer is yes. Okay, this, since most of you are from biotechnology and pharm, B pharm, I'm sure you recognize this is a DNA molecule. Okay, this is the DNA molecule, and the breadth, this breadth over here is around 10 nanometer. Okay, this is around 10 nanometer. Okay, now if you go back again, try to zoom in. Okay, here you see that there are these molecules here. Okay, let's clear the names. here, if you look at this square, okay, this atom is roughly of the size of 1 nanometer. Okay, now we are coming towards the lower end of the definition. Okay, so again I go back to the definition is of nanotechnology was from 1 to 100 nanometer. Okay, this is the lowest level we have come to. Okay, now have you noticed something? Okay, have you noticed something when we go from the first images to this image? Okay, what do you notice? Somebody write, what do you notice that you, when you go from this image to this, from this image to this one? Yes, we are zooming in objects, but something more. Okay, but okay, no worries. Yes, some, I think Naman Sangvi has written it's monochromatic, it's black and white. Okay, so very important. This is a good answer that you have observed. Here, the reason why we are seeing colored image is that this is the light microscope that you're using. Okay, let me write it down. Light microscope. You're using a light microscope to see this object. Okay, but then when you zoom in more, you cannot see this using light microscope. Okay, you need something called let me write it again. Electron microscope. Electron microscope. Okay, something called electron microscope. Okay, great. Somebody has written something. Okay, some people have already written about electron microscope. That's okay, good. So let's clear. We will go into this difference between light microscope and electron microscope later. But for now, for first class, we leave it here. Okay. Just one sec. Okay. Now, another observation can you make from this image to this image? Similar observation. What is the difference when you go from this image to this image? Okay, I have no answer, but it's okay, no problem. So here, this is a real image. Yes, I understand it's a structure of DNA. We have already talked about it, but something else. Here, this is a real image, okay? Image that has been taken by someone, okay? But as soon as we go here, this is not a real image. This is a computational model, okay? This is not a real image. People have computed this in the computer and they have restructured to make this DNA model, okay? Similarly here, okay? So why are we not doing similar similar imaging of DNA molecules or even a molecule here? Here you are seeing these atoms. These are not real atoms. These are simulated models. Okay. So the reason here is that even electron microscope has some limitations. Okay, you can actually see 10 nanometer objects. Okay, but because this is the example here is a biological object, sometimes it's difficult to see it. Okay, that's why there are two different electron microscope. One is the scan electron microscope that is used here, and to see molecules, okay, you need even very powerful electron microscope called transmission electron microscope. Okay, let me draw transmission electron microscope. Okay, this is much more costly. It's at least the worst electron transmission electron microscope is at least 10 crore rupees. Okay, and very few universities in India have it. Okay, I think there are very good ones in ISC Bangalore and in IITs, some of the IITs, but this is a very costly instrument. Okay, yet sometimes you need to use simulated models to confirm what you have seen is true or not, even in transmission electron microscope. And we'll learn more about it later. Okay, now let's go ahead. So, does size matter or not? Okay, it's not how big you are, it's what you do with it, right? Okay, so let's summarize what we had seen till now. Okay, please remember this diagram. Okay, this diagram will help you to understand where you are. Okay, here there are few important things to remember here. I hope you can see the full screen. Okay, so the scale is here is in nanometer. Okay, the unit is nanometer. As far as our definition, our definition of nanotechnology, we should be somewhere in between this region. Okay, sorry. Around this region. Okay, this is where we operate. Okay, other than that, we don't operate in these regions. Let me change color. We don't operate in these regions. We don't operate here, and we don't operate here. Okay, we don't. Okay, so what are the things we don't operate in? Okay, so this is a tennis ball, and this is 100 million nanometer. Okay, we are not working here. Okay, this is a dot. You know, whenever you're writing with your hand, or you put a dot after a sentence when you are writing English, then you put this dot. That small dot is roughly around here 1 million nanometer. Okay, this is a cancer cell in your body. Okay, this you have to remember, for especially for understanding nanobiotechnology, you have to understand this, that the bacteria and the cancer cell are always bigger than the nano objects that we are fabricating. Okay, why? We will understand. Okay, but this is what at this point you have to remember. This is where the bacteria and the cancer cells are here. Okay, they fall in the 1,000 nanometer to around 50,000 nanometer. 50,000 nanometer is roughly around 50 micrometer. Okay, and remember one thing, bacteria is even smaller. Okay, and even smaller than bacteria is what? This is a virus. Okay, so at this point you should remember is that the coronavirus is somewhere. Why is it so dangerous? Why are we wearing masks, which is especially N95? Okay, that's because generally the mask that we were using before, it was good enough to protect us from dust. Okay, before the pandemic, corona pandemic, people were using very few people are using masks, and they were using it to stop bacteria or any kind of pollution to go through their nose. Okay, but then after the pandemic, people started making N95 masks. Okay, why? Because the virus is smaller than the the bacteria or pollution that is existing in the cities. Okay, so that's why special masks had to be made. Okay, But our nanomedicine or nano objects that we're going to make is even smaller than the viruses. Okay, this is what you have to remember. Okay, that the nano objects we are making are smaller than the living organisms that are present in nature. Okay, very important to note. But it is not smaller than the molecules like water or glucose. Okay, if you look at here, glucose is roughly around 1 nanometer or maybe even less. Okay, this is a water molecule here. This is a water molecule here. The water molecule is much smaller than the nanostructures that we are making. Okay, somebody has any questions? Okay, do you have any question at this moment? Because this is a very important graph that you have to remember. So if you have questions, please write it in the chat box before I go ahead. Has everybody understood, right? Yes or no? Okay, okay, great. Okay, if somebody has not did not understand anything, please write and please ask me to repeat it if somebody has not understood, because this graph has to be there like a memory in your brain if you want to know about in future. Okay, Abhishek says please repeat. Okay, Abhishek, I'll just go through it very fast. Okay, so this yellow range, the yellow double-headed arrow that you see, this is the range that falls under the definition of nanotechnology. Okay, this is the range in which we are going to make devices or any structures when we call nano device. Okay, and these devices are always smaller than the living organisms. Okay, like virus, bacteria. This is cell. Cancer cell is also somewhat similar to body cells we have. Okay, they are in the micron region. Okay, that's why the point at this point to remember is that nanostructures will be smaller than the living cells, but they are bigger than the molecules. Okay, like water, glucose, proteins. Okay, sometimes proteins are big, but many of the small alcohol molecules or any kind of molecules, they are smaller, much smaller than the nano devices. Okay, great. So I'll move ahead. So here is another important thing to remember is that what is the size of atom? Okay, we talked about molecule, which is roughly around in this case 0.1 nanometer. Okay, or even bigger, but the atom is roughly of generally 0.3 nanometer. Okay, this is quite a big atom. Okay, and this is not the reason we are working on. Okay, but you have to remember it. Okay, but there are also times you have to remember that this is a carbon chain. Okay, what is the distance between two carbon atoms? Okay, suppose in a ring structure or in a graphite structure, what is the distance between two carbon atoms? Okay, you have to remember this range. Okay, this small range will play a very important role in future. Okay, double DNA structure, what's the diameter? It's roughly, we already talked about 2 nanometer. Bacterium, okay, 200 nanometer. It's bigger than the nano devices that we are making. Again, red blood cells, RBC, that you can use that I'm sure everyone have seen it in their school days at least. 6,000 nanometer. This is the human hair. 80,000 nanometer. Okay, 80 micrometer. 80,000 nanometer is equal to 80 micrometer. Okay, So this is a picture that is always shown in introductory classes. This is a human hair that from your head. Okay, that's the human hair. And if you see here, this is a called nanofiber. Maybe I should zoom in a bit. The small fibers that you see, compared to the human hair, it's very small. Okay, much smaller. And this is like a huge giant human hair, but of course it's very small, you know it. Okay. So what are the areas that nanotechnology is being applied today? Okay, we should know. So at present, we will specifically talk about biotechnology. Okay, in the later classes after we finish the basics understanding. Okay, but besides biology, there is also transportation. In transportation, we already talked about the bike. Okay, it's very costly, but people are using in it. Okay, they are also making the F1 car, you know, the Formula One racing car. The structure they are using nanotechnology to make it light and very strong. Okay, national security and defense. Okay, this is one of the most important. I mean, every country is spending a lot of money in this field. Why? Because using nanotechnology, you are getting small robots or even semiconductors, which are much more powerful than the those available in the market, and they can be very helpful. And people are trying to make quantum computers, but for that you need a physical structure as well. The semiconductor devices, those come under national security and defense. Food and agriculture. Okay, especially related to preservation of food. Okay, people are trying to use nanotechnology. In Hyderabad, there is a company called not a company, it's institute. It's called ARCI. I forgot the full form, but they are trying to make the water purifying candles using nanotechnology. Okay, medicine and health. We will talk in detail. Okay, in the later classes, we'll read some what do you call research papers and try to understand what is how it is applied in medicine, especially aerospace. I already talked transportation, energy and environment. Okay, at present there is a huge trust in solar cells. Okay, to green energy. Okay, people all over the world, governments are putting a lot of money in the sector of solar cell or green energy. Okay, but these solar cells, if you look the present ones, the silicon ones, okay, their efficiency is just around 12 to 15%. Okay, of course 12 to 15% is the starting. Okay, once you buy it, it gets 12 to 15% efficiency, and then after like 5 years, 10 years, this efficiency will decrease. Okay, but if you look at the solar cells that are used in the satellites, you see the satellites, how do they gain energy? They have solar panels, they are close together. Once they put in the orbit, they open up. Okay, those are very special solar cells. Okay, there they use nanotechnology, and those are costly, but they give efficiency around 40%, 45%. Okay, multi-layer solar cells, costly, but it very good, very high efficiency. Advanced materials and textiles. Okay, you'll find a lot of information about how people are using nanotechnology that is integrated with your clothes that you're wearing, the normal clothes that are wearing, and these clothes do not become dirty. Okay, so the dirt in the clothes do not stick to the cloth. Okay, if a cup of chai or tea falls on your cloth, it just goes away. It's like you can make your clothes hydrophobic in nature. Okay, We'll talk about hydrophobicity today. Somebody wrote like in in Mars rover. Yes, yes. Solar Sense in the Mars rover also has very high efficiency solar cells, not the ones that we use at home. Okay. Next, okay. So we will also go in more details about why we get this kind of properties. But here is an example. Okay, what is the color of gold that you see? Okay, in India, people like to wear gold rings or gold chains. Okay, generally, the color is something like this one here. Okay, it's a gold ring, yellow in color or something like that. Okay, but if you go to nano dimension, okay, this is a gold ring. Okay, if you go to nano dimension, roughly around 10 nanometer diameter, then this same gold ring, okay, which is yellow in color in bulk material, becomes green. Okay, and then if you go to 1 nanometer, it becomes red in color. Okay, so this gold ring in which is red in color, you will never get in bulk material. Okay, we will, in this course, we will show how to make gold particles of different colors. Okay, I will show some videos also, and I will show the science behind making gold particles of different colors. Okay, and how you can control them, how people are making it at present. Okay, and why does the color change? Okay, that's also very important. The reason cannot be because the size is small, that's why the color changed. No, I mean, that is for people who are not in nanotechnology, who are not learning science, it's okay. But people who are studying seriously, are already taking master's course in different fields, they should know why that color changed. Okay, then also we will talk about graphite. Okay, this is the graphite that you have normally used while drawing with pencil or writing with pencil. This is the graphite. Okay, it has certain properties. Okay, but same material. Okay, you change the structure like a buckyball or a nanotube. Okay, this they can become from semiconducting to metallic to even insulator. Okay, so these properties that you can find in nano objects is not available when they're in bulk form. Somebody wrote like coal and diamond. I did not understand the context, but okay. So properties of nanomaterial. Here, okay, Revenant, yes, then like molecular formations. Coal is nothing but carbon, okay, but diamond is also carbon, but in certain specific arrangement of the carbon atoms, which gives different properties. It becomes more transparent, very hard, and has more crystalline structure. So properties of nanomaterials. So materials reduced to nanoscale can show different properties compared to what they exhibit in macro scale. Okay, this is, for example, opaque substances can become transparent, like in copper. We will show how. Stable materials can turn combustible. Okay, aluminum is very widely used. You know, sometimes when we are buying sweets in sweet shops, they put a aluminum foil. Okay, I'm sure many of you have used aluminum foil to pack your food. Okay, so you can use this aluminum foil because it's a stable material. It will not react with your food. Okay, but there is an Indian company called Log9 Materials. Okay, they are making batteries which are made of aluminum, and that because why? Because the aluminum is in they have made is in nanomaterial, and when it is in nanomaterial, it can react with oxygen from the air, and then you can produce electricity. Okay, so bulk aluminum is stable. That's why we use it in the food. Okay, to wrap our food. Sometimes we can heat it in the oven also, aluminum foil. But nanomaterial aluminum is very reactive, and there is an Indian company called Log9 Materials that are making batteries out of it. Insulators becomes conductors. Okay, we will go more depth. Even the carbon nanotubes, sometimes they can be semiconducting. They can become also in a conductor. Silicon, which is generally a insulator, it can become, you can make it conducting by making silicon nanomaterials. Solids turn to liquids in room temperature. Gold. I mean, we'll talk about, we have separate lecture about gold nanoparticles. Yes, this is a very important point to understand, is that nanomaterials tend to become more chemically reactive than ordinary sized counterparts. Okay, because they have more surface area. This is something we have to understand very carefully, because this is the property not all, but many of the scientists use to get novel properties. Okay, so what does it mean? An increase in surface area to volume ratio. Okay, this is the part you have to remember. Increase in surface area to volume ratio. Okay, you can some people argue that if you have a bigger ball, you have a bigger surface area. Okay, if you have a smaller ball, you have a smaller surface area. So why are we talking that nanomaterials should have smaller, bigger surface area? Okay, it's a wrong way of thinking. Nanomaterials have smaller surface area, but they have a higher surface area to volume ratio. This is the correct statement. This ratio will increase. How it increases, we will show you in the next slide. Okay, because of this increase in ratio, it alters the mechanical, thermal, and catalytic properties of materials. Okay. So we want to show how surface area to volume increases. Okay. Now look at this cube. Okay. This length is 1 meter, height is 1 meter, and also the breadth is also 1 meter. Okay. Everything here is 1 meter. Okay. This cube. Okay. Okay. Now, the second cube, what you have done is that you have made some cuts. The same, exactly the same cube. Okay. You have made some cuts. Okay. You have cut it in 6 ways, 3 ways. You have made one cut here. Okay. Made another cut here, and then the third cut here. Okay, so once you cut this in 3 different sides, you get something like this. Okay, this is the second cube. Okay, so the volume has not changed at all. Okay, same cube, you just have cut it. Okay, and then as a result, you have got 8 smaller cubes. Okay, this is clear, right? Yes. If have you understood what I have just said? This is a very important concept to understand. Okay, okay. Okay, so it seems everybody has understood. So what is the area of this first cube? Okay, the area is, there are 6 sides to the cube, and 6 into 1 meter square is 6 meters square. Okay, and the volume is 1 meter cube, because every side is 1 meter. Okay, now let's look at the smaller cube, the second cube. Okay, so in the second cube, this is only half the size. So this was 1 meter, so this will be half meter. This is only half meter on all the three sides. Okay, so the total area of this half into half, okay, into 6. Okay, that's me. Okay, first you calculate this. This is the area of a single half meter cube. Okay, half into half, one side into 6 sides. That is okay, and then after that there are 8 cubes, so you multiply by 8 here because there are 8 cubes. So the total comes out to be 12 meters square. Okay, so you put this 12 back in this equation. Okay, surface area to volume ratio. Okay, and then since we cut the same cube in 3 parts, the total volume remains same. Okay, the volume here, let me just change the color. This volume here, because it's the same cube, has remained same. Okay, so but what has changed is this value here. This value here. Okay, before this, this was the this is the surface area. This is the ratio of surface area to volume. Okay, surface area to volume. So here it is 6 meters square by volume, which is meter cube. Okay, but the same, after we made this same cube smaller in 8 parts, the surface area to volume has increased, but 2 times. It has become 12 meters square. Okay, so what we have seen is that when we cut the when we decrease the size of the bulk material into smaller particles, we are starting to increase the surface area compared to the volume. Okay, or the surface area to volume ratio. This is what we are increasing. Okay, at this point. Okay, right, yes, if you have understood this concept, because this is the fundamental basic point to understand. Okay, if you don't understand this concept, everything else in future will be not understood. Okay, I don't mind repeating it, but please, if you have not understood this, I'm ready to repeat it, but repeat. Okay, somebody, Revnath has said repeat. Okay, I'll repeat. Don't worry. This is if you understand this concept, you will go very far. Okay, so this is very important. And this is one of the basic questions sometimes people ask in the interviews as well. Okay, when you apply for interviews for some either to do PhD in some other colleges or abroad, or maybe to some company as well, this is what they will ask you. Okay, so generally they ask you is that if you have a bigger ball, the surface area is big. If you have a smaller ball, the surface area is small. Okay, so why are we saying that the surface area to volume ratio will increase? Okay, what is increasing? Okay, so what is important here is that there are two cubes here. This is 1, okay, and this is 2. Okay, cube number 1, cube number 2. Okay, so the cube number 1 has 1 meter cube. I mean, everything is 1 meter. So the surface area it can be, if you calculate for one side, is 1 meter square into 6 sides. So its total is 6 meter square. Okay, so your surface area for cube number 1 is 6 meter square. The volume, so 1 meter into 1 meter into 1 meter is 1 meter cube. So the surface area to volume is 6 meters square divided by meter cube. Okay, now you take this cube, okay, you make it small. The blue lines that you see is the way you have taken a knife and you have cut it. Okay, you cut this 1 meter cube with a knife in these 3 lines, 1, 2, and 3. Okay, once you cut it, you will get this 8 different smaller cubes. Okay, and you have cut it in exactly in half. Okay, not in random way. Okay, exactly half, so that this distance here, this distance here, everything is half. Everything here is half. Okay, everything here is half, the smaller cubes. So how to calculate the surface area of these 8 cubes? Okay, so surface area is A into B, so half meter square into half meter square, and one small cube has 6 sides. Okay, so in multiply by 6. Okay, and then this 8 it comes because there are 8 different cubes. Okay, in this case there is only one cube, that's why we do not write into 1, but here there are 8 different cubes. So 8 different cubes has total area of total area of 12 meters square. Okay, 12 meters square. So this 12 you put it in this equation here. Okay, so 12 meters square, and total volume of this all the cubes is what? Okay, is the same cube that we have cut it. Okay, the volume remains same, so it's 1 meter cube. Okay, so now the surface area to the volume has doubled from 6, it has become 12 now. Okay, you have only thing you have done to the cube number 1 is that you have cut it in 3 parts. You made 3 different slices and you produce 8 cubes. Okay, just because you cut it in 8 parts, the surface area to volume has increased. Okay, this is what we have to show to people, that although the surface area of individual cube has decreased, okay, but the overall surface area to the volume of the material has increased. Okay, have you understood? Okay, now is it okay? Right, yes or no in the chat box. Okay. Revant, is it okay? Okay, great. This is very important to understand. Okay, I'm clearing on this. Okay, nobody is saying no, it's okay. So next is another way of thinking. Okay, exactly the same thing is just another example. Okay, each individual cube is about 1 centimeter. Okay, this is the sugar cube that you have. Okay, so if you have sugar cube of this size, so one surface area to volume ratio of one sugar cube will be 6 centimeter square by centimeter cube. Okay, imagine one cube here is 1 centimeter. Okay, now you take these small blocks, okay, 64 blocks of sugar cubes, and put it on top. Okay, and then you calculate this surface area. The surface area will be something like 6 into 16 centimeters square, because there are 4. Okay, 4 into 4, 16. Okay, I'll show you how is 4 into 4. There are 4 here, 4 here. Okay, 16 centimeters square. Okay, volume will be 64 centimeter cube. And if you take this surface area 96 divided sorry 64 sorry 96 divided by 64, you get 1.5 centimeter square by centimeter cube. Okay, if you join all the sugar cubes, this is the surface area to volume ratio. But if you don't, if you take the single block of a single cube of sugar cube, the surface area to volume is 6. Okay, this is the same example. Okay, in the previous example we cut the cube. In this example you take the smaller cubes and make a big one. Okay, they're showing the reverse way of doing it. Okay. So what is the effect of this phenomena in living beings? Okay, does it also affect this? Does this phenomena also affect living forms or not? So here, if you see, this is a mouse. Okay, very small. Okay, so this mouse is very susceptible to the heat changes. Okay, because why? What is the reason? Because here it has a larger surface area to the volume. Okay, so what happens? So what the mouse has the largest surface area to the volume ratio. Okay, it means how do we lose heat from our body? Okay, when it is very hot in the summer, we lose heat from our body from our body surface, from our skin. Okay, so the amount of surface area this guy has, okay, is very, compared to the volume, is very high. So in the summertime, the amount of heat it will receive is very high. In the winter time, amount of heat it will lose compared to the volume ratio, it will be very high. Okay, so that's why this is very susceptible to the changes in the heat. On the other hand, a bear, okay, the bear also feels hot. Okay, but it is able to bear it because the volume is giving a lot of protection. Okay, the volume, there is a huge amount of mass in the body which is compensating for the amount of loss or gain of the heat, so it's less susceptible to the heat changes. Okay, this here because of the larger surface area to the volume ratio, the effect of the change is much more higher compared to the bear. Okay. As far as this example, have you understood it? Because this is also a very important example. Okay, anybody wants me to repeat? It's not very intuitive, it's sometimes counterintuitive. Okay, since people, okay, if you want me to repeat, please write repeat. Okay, nobody is writing repeat, so I go ahead. So nanostructures and nanomaterials exhibit properties which are different from macroscale, which we have seen. Okay, they are macroscale counterparts, which they are calling it big brother. Okay, mechanical strength. Okay, what are the changes that you can see? Mechanical strength, how do they break? How hard they are to break? Okay, electrical conductivity. Okay, we will see in future how fast the electrons flow through them. Okay, is graphite electrically conducting or insulating? Can you write? Graphite, the pencil that you use, is it insulator or conducting, or is it semiconducting? Okay, somebody is writing conducting, insulating, semiconducting, all kinds of answer. Okay, generally the graphite that we use is it's very insulating, okay, because I think I don't know if you will see that structure today. Yes, probably not, but it's very insulating. Okay, if there is a pure graphite from the volcano, very rare, okay, and very small, microscopic, okay, that can be conducting in unidirectional way. Okay, I will show it in the later classes, but in general, graphite is very insulating. Okay. So thermal conductivity, how fast the heat electrons, heat flows through them. Okay, this is another thing. Chemical activity. Okay, this is very important to remember, the one in the red. Okay, highest surface area to volume ratio leads to higher chemical activity. Okay, you should remember this. This is one of the golden statements. This is one of the phenomena that is used to cure cancer in using nano biomedicine. Okay, transparency. Okay, we can. I think we have already seen one example. You can make it transparent. Magnetism. Okay, we will see it in the nanomedicine class how magnetism is used, and for we will see how nanomagnetism is used to take the nanomedicine from your blood to the exact cancer cell and deposit this medicine inside the cancer cell. Okay, many people are using magnetism to uh, to deliver the nanomedicine. Okay, so this is also very important to remember. It's called nano. How do you classify? Okay, we have already seen the definition of nanotechnology or nanomaterials, but we also need to classify. Okay, so first is nanoparticles or nanospheres. Okay, you understand sphere is like a ball, but here is nanosphere. Okay, this is called 0D. Okay, it has 0 dimension. Okay, nanoscale lengths are measured in all 3 dimensions. Example, buckyball. Okay, let me go to find some. Okay, let's finish this definition. We'll go to the examples. Okay, it's called 0D. Okay, here you should remember all the 3 lengths, all the 3 lengths in the 3 dimensions are in nanoscale. Okay, it's a small nanometer, it's a nanoball. So in all 3 directions, it is in nanoscale. Nanotube or nanowire or nanorod. Okay, it's called 1D. Okay, why 1D? Okay, maybe it's better to draw it. Okay, so wait. So nanotube or something like this. Okay. So what happens is that this is a tube. Okay. So nanoscale lengths are measured in 2 dimensions. Okay. The third dimension is in micrometer or more than the definition of nanomaterial. So this dimension here, okay, maybe in different color. This dimension here, okay. This dimension here, it is not in nanoscale. Yeah. Not in nanoscale. Okay, the green arrow that you can see, this is not in nanoscale. Okay, but these dimensions, this here and here, X and Y. Okay, these are in nano dimensions. Okay, these here are in nano dimensions. Okay, so one of the dimension is not in nanoscale. Okay, that's why it's called 1D. Okay, this is very important. Have you got it? Anybody wants me to repeat this one? Understood. Okay, okay, great. Okay, now comes nanoscale thin film or ultra thin film. Okay, or 2D. Okay, so what is 2D material? Okay, let me draw it again. Okay. Okay, so I'm just trying to draw here. Okay. Okay, so in this case, these two dimensions are not in nanoscale. Okay, they are, again I'm saying it's not. Okay, not in nanoscale. Okay, but the third one here, this small third one here, this one, this is only, this one is in nanoscale, this one. Okay, that's why it's called 2D. Okay, got it? Okay, no problem till now? No problem. Does anybody have problem, write problem in the repeat, if somebody wants me to repeat? Okay, nobody has repeat, so I go ahead. How to, okay, how to know which should be nanoscale or not? It's not how to know which should be nanoscale or not. Suppose they give you a diagram and they give you the dimensions. Okay, then you should be able to classify whether they're 0D, 1D, 2D. Now we will talk about 3D also. Okay, so if we continue the definition of this classification, we should not have something called 3D. Okay, in 3D it should be a bulk material. Okay, isn't it? None of here in the first case, all the 3 dimensions, in this case, all the 3 dimensions are in nanoscale. Okay, in the second case, only one of the direction is not in nanoscale. Okay, in the second case, 2 of the 3 directions are not in nanoscale, but in 3D, none of the, if we go continue the same way, it should be that none of the 3 dimensions are in nanoscale. So we should have, there should be no nano 3D objects. Okay, if we think that way. Okay, but there are two, in fact there are 2 different kinds of nano 3D objects. Okay, these are called nano composites. Okay, so what happens is, what is a composite? Suppose you mix 2 different objects, for example, nanotube and nanofilm. Okay, so you have a nanofilm, and then on top you put some nanotubes. Okay, you're putting some nanotubes. Okay, and then again you are putting some on top. Again you are putting some uh, another thin film. Okay, after that, let's say you're putting some second layer of nanotube. Okay, so you have got a 3D material. Okay, you got a 3D material, but there are two different components. Okay, one of them is a nanotube. Okay, one of them is a nanotube here. Okay, one of them is a nanotube and another is a thin film. Okay, so it's not a single material. Okay, just like this, you have to focus on this word here. It's called composite. Okay, composite means you are mixing 2-3 different materials. Like when you're building a building, okay, you have this iron rods and then you put the bricks and then you put the cement. Okay, 3 different materials. Okay, you are getting 3 different properties in the same object finally. Okay, similarly, nano composite, you are mixing and matching different kinds of material. Okay, to get a nano 3D composite. Okay, similarly, there can also be okay, did you get this nano composite? Ask me to repeat if you want me to repeat nano composite. Okay, nobody has written to repeat, so I go ahead. Okay. Then there is something called nano 3D structure. Okay, so these are very unique structures that can be measured in nanoscale. Let's see if I have a drawing at present. Yes, here. So I'm going to ask you a question now. Okay. So what is this 1D? My first question, right into the chat box. What is this 1D, 2D, 3D? Please write in the chat box. Or 0D, whatever. Okay. Oh, somebody wrote 2D. Okay. Anybody else? There are 87 of you. Please write the answer if you are present. Okay. So the answer is 1D. So Sweta and those Taslim, Taboli, and somebody else also has written 2D. This is a 1D structure. Why? Only one of the dimensions. Okay, I just repeat it. Only this dimension here is not in nanoscale. Okay. Otherwise, if you look at the height and also the breadth, okay, these structures, okay, these two dimensions are in nanoscale. That's why it is in it's a these two dimensions are in nanoscale, except this is not in nanoscale. Okay, only one of them is not in nanoscale. Okay, that's why it's called 1D. Okay, what about this structure? What do you think about this structure? The second one, this one. Okay, great. Okay, so I think everybody has written 2D. So my next question is, which dimension is in nanoscale? Length, breadth, height, which dimension is in? Okay. Now somebody wrote no. Okay. So I'm saying that this is the length L, this is the breadth, and then there is the height. Okay. So for those who have written height, that's the correct answer. This length, okay, this length here L and the breadth, they are not in nanoscale. Okay, only the height. This is one atomic thin sheet. Okay, this is in nanoscale. Okay, because what is graphene is that you have taken this graphite, you have just taken one slice of this thing and come here. Okay, what is this structure? This one and this one, according to the classification. Shruti, she has asked, how do you know which side is it? Which side is in nanoscale? I mean, I'm at present, I'm just making an assumption because remember I had told you that you should know the distance between two atoms in a carbon material. So it was 0.15 nanometer. So imagine if you have limitless, if the L is very, very big, okay, and B is very big, so it crosses the nanoscale dimension. Okay, so this blue structures that I have shown, what is it? Please, only one answer. What do you think it is? 0D, 2D, 3D, 3D, then which 3D? Don't write. In 3D, there are two, I said, composites or 3D structure. There were, okay, let's go back to the 3D definition. 3D, there was nano composite and nanostructured materials. So the blue falls in which of them? Maybe I should zoom it some for, okay, can you see it better? Let's make the clear drawings. I'm talking about this and this. Okay, so it is not nanocomposite. Okay, if you look here, they're made of one material. Okay, compared this is a 3D material. This is a 3D material. Okay, there are graphene sheets. Okay, graphene sheets, and there are nanotubes. Two different material coming together and forming 3D material. It forms a composite. Okay, but here, if you look carefully, it's one material. Okay, at the joint, if you look at the joint, okay, if you look at these joints here, if you look carefully at these joints, they are made of same material. They're all connected. If you look at these joints here, okay, they're all connected. So it's a 3D nanostructure. Okay, and in this case, there are two different materials. This is one material, and this is another material. Okay, if you look at the red ones, these are graphene, and if you look at the green ones here, these green ones here, this is another material. Okay, in this case, this is only yellow material, which means this made of only one kind of material, but it is 3D. So it's a 3D structured nanomaterial, and in this case, it's a two different material forming into 3Ds. So it's a 3D nanostructured, 3D composite material, because there are two different types of material. Okay, have you understood this part? Is it okay? Right? Yes or no, please. Okay. Okay. Looks yes to me till now. Okay. So for today's class, we will finish here, but let me just give you a just glimpse of what we will do in future, especially related to nanomedicine. Okay, just give me 1 sec, don't leave. So in future, we'll talk about targeted inorganic nano device for breast cancer therapy and diagnosis. So there are two things here. Diagnosis, also we are using nanoparticles, and also for therapy. Okay, so if you diagnose some cancer problem or any kind of problem very fast, okay, and using nanomaterials, you can discover the disease very early. Okay, it helps to cure the disease better. Okay, so we will talk about drug delivery. Okay, how antibody is attached to the nanoparticle. Okay, MRI contrast reagent, means you have heard about MRI, right? Okay, MRI machines. Okay, so they use certain contrast agents to make the specific area very bright to the magnetic rays. Okay, so if you can improve the contrast of this using nanoparticles, and in this case they use magnetic nanoparticles, okay, you can detect the disease much better. Okay, then there's photothermal therapy. Okay, sometimes you excite the nanoparticle in such a way that after it de-excites, it releases some heat, and because of that heat, either you kill the cancer cell directly, or you release certain medicine into that cancer cells, and then only those cancer cells will die. Okay, and there is also the gene therapy. Will not go much in that, but we'll go much more deeper in drug delivery, MRI constant contrast reagent. Okay, so let's have a look if I can have a diagram. Okay, okay, here you can see we have injected a mice with certain drugs. Okay, and then you'll see that only that region where these cancer cells are present, that is become very visible under the MRI machine. Okay, sometimes this is not visible if you don't use nanoparticles. Okay, so this kind of work we will see. Let's see again here. Okay. Okay, so maybe I will stop here. So there are a lot of people who have not registered for today's class, but if you want to know more about drug delivery and how it can improve the nanomedicine field, we will go into it. Today we just did the basics. Okay, if we don't do the basics today in the beginning of the class, we will not understand. Okay, because towards the end of the class, I will ask you to read research papers. Okay, I will go with you, but I'll also ask you to read. Okay, so when people read the research papers, if you don't have the basic, everything else is just a just another course that you have taken. Okay, I want people to understand, so that's why I'm focusing on the basics. and then we'll go and understand how to use this kind of nanotechnology for therapy. So if you have not registered, please go ahead if you want to take the full course. Okay. Is that all right for today? Right? Yes or no? Okay. Okay. If you have questions about today's slides, you can ask me tomorrow. Okay. Great. Great. Okay. Thank you very much, and enjoy your evening. And if possible, go through the slides. I think you can access the video. Okay. Have a nice evening.